Something crossed into our solar system from the darkness between stars, and it carried a secret that changes everything we thought we understood about the universe. It was not from here, not from our sun, not from our planets, not from anything that has ever belonged to us. It came from somewhere so ancient, so radically different, so impossibly cold, that scientists are still struggling to process what it means. James Webb Space Telescope looked directly at this visitor. And what it found did not just surprise the scientific community. It rewrote the story of where we came from and what else might be out there. There are moments in science when the universe stops being a backdrop and becomes a message. When something happens, not in a laboratory, not in a simulation, not in a theoretical model, but in the sky above your head. Something real and physical and incomprehensibly ancient. And the message it carries is so enormous that the people who dedicated their lives to understanding the cosmos have to stop, look at each other, and quietly admit that the textbooks were incomplete. July 1st, 2025 was one of those moments, and most of the world missed it entirely. On that day, a survey telescope called ATLAS, the Asteroid Terrestrial Impact Last Alert System, detected something moving through our sky. Something with an orbit so extreme, so hyperbolic, so fundamentally incompatible with having originated in our solar system that astronomers immediately recognized it for what it was, a visitor from another star. Not a metaphor, not a theory, a literal object, composed of ice and dust and ancient chemical compounds that formed around a different sun, in a different planetary system, in a completely different region of the galaxy, and had been traveling through the cold, dark void of interstellar space for so long that our solar system was not yet born when its journey began. It was designated 3IATLAS, the third interstellar object ever identified, and the James Webb Space Telescope was about to look directly at it. 3IATLAS is only the third confirmed object ever found to be drifting through our solar system that originated around another star. The first two were 1I Oumuamua, discovered in 2017, and 2I Borisov, detected in 2019. 3 objects. 3 visitors from the interstellar void, each one a physical piece of another planetary system delivered to our cosmic doorstep. Each one a specimen of alien chemistry, alien formation, alien history, arriving in our solar system briefly, passing through, and then disappearing forever back into the dark. The window to study any of them is narrow. Once they pass our sun and begin their journey outward, they will never return. They are passing through on a one-way trajectory across the galaxy, and if you miss the opportunity to observe them, that opportunity is gone forever. So when 3IATLAS appeared in the summer of 2025, every major telescope on Earth and in orbit pivoted toward it with an urgency that is rarely seen in astronomy. NASA's James Webb Space Telescope observed interstellar comet 3IATLAS on August 6, 2025, using its near-infrared spectrograph instrument. A host of NASA missions came together to observe this interstellar object before it left forever. Webb was joined by Hubble, by the Spherex Observatory, by ground-based telescopes, from Chile to Hawaii, by the European Southern Observatory's Very Large Telescope. An international scientific response of extraordinary scale, coordinated around the brief window when this ancient traveler was close enough and warm enough from the sun's heat to reveal its secrets. Because what makes comets ideal for chemical analysis is exactly what makes the window so short. When a comet approaches the sun, the heat vaporizes its surface ices. That's sublimated. Material forms a glowing cloud around the nucleus called a coma, and that coma is an open book written in chemistry, a direct readout of what the comet is made of, where it came from, and under what conditions it formed. You just need the right instrument to read it. NASA's James Webb Space Telescope collected the first mid-infrared chemical fingerprint of an interstellar object during its observations of 3IATLAS. Think about what that phrase means, mid-infrared chemical fingerprint. Webb did not just take a picture. It did not merely confirm the object's existence or measure its size. It performed spectroscopy, breaking the light coming from the comet's coma into its component wavelengths, each wavelength corresponding to a specific molecule, each molecule telling a specific story about where this object was born and what its home planetary system looked like billions of years ago. And what the fingerprint revealed was unlike anything scientists had ever seen from a comet that originated in our solar system. Astronomers used Webb and its near-infrared spectrograph instrument to identify carbon dioxide, water, water ice, carbon monoxide, and carbonyl sulfide in the comet's coma. Those molecules, in isolation, are not shocking. Many of our own solar system's comets contain similar compounds. But then the ratios came in, and the ratios changed everything. What was not expected was the highest ratio of carbon dioxide to water ever observed in a comet. In solar system comets, water dominates. It is the most abundant volatile, the primary driver of activity, the molecule that defines how a comet behaves as it approaches the sun. Carbon dioxide is present, but it is secondary. In 3IATLAS, the balance was dramatically different. Carbon dioxide was not a secondary player. It was a dominant one. Webb's observations confirmed that 3IATLAS releases far more carbon dioxide relative to water when compared to typical solar system comets. This is not a minor statistical variation. This is a fundamental chemical signature pointing to a formation environment where the conditions that shaped molecular abundances were radically different from the conditions in our own solar nebula 4.5 billion years ago. The comet was not built the same way our comets were built, because it was not built in the same place, around the same kind of star, under the same kind of physics. Using Webb's MIRI, the mid-infrared instrument, the research team conducted 2 sets of follow-up observations in December 2025 as 3IATLAS retreated from the sun. The first observation ran December 15th to 16, when the comet was approximately 329 million kilometers from the sun. The second came December 27th, by which time it had moved out to roughly 379 million kilometers. These were critical observations. When a comet is inbound, approaching the sun for the first time, its outermost surface layers are doing the talking. But those outer layers have spent billions of years exposed to cosmic radiation in interstellar space. They are processed, altered, chemically modified by the relentless bombardment of galactic cosmic rays during the long journey between stars. To get at the comet's true interior composition, the pristine, ancient material it has been carrying since the day it formed, you need to wait until the sun's heat has burned away those irradiated outer layers and started sublimating the untouched interior. That is exactly what the December observations captured. The Webb observations revealed that Comet 3IATLAS is rich in methane, and this is the first time scientists have ever detected methane on an interstellar object. 3 interstellar visitors have now passed through our solar system. This is the first time any of them has revealed methane. And the fact that it was not detected during the inbound phase, when the comet was still wearing its irradiated outer shell, but only after the sun had stripped those layers away, means the methane was buried deep inside. It was preserved, sealed away from the cosmic radiation of interstellar space, intact since the moment the comet formed. What Webb detected in December 2025 was not surface chemistry modified by billions of years of radiation. It was the original interior of an object born in another planetary system, preserved across geological ages, delivered to our neighborhood, and read by the most powerful space telescope humanity has ever built. The methane discovery matters for a reason that goes beyond chemistry. Methane is a volatile molecule. It is extremely sensitive to temperature. For methane to survive inside a comet's nucleus over timescales of billions of years, the formation environment must have been extraordinarily cold. Cold enough to freeze methane solid and hold it there against everything the universe throws at it during a journey across the galaxy. Researchers believe that the planetary system where 3IATLAS originated was incredibly cold. The temperature in the formation environment of 3IATLAS was less than 30 Kelvin, which corresponds to approximately minus 243 degrees Celsius, colder than almost anything in our own solar system's formation history. 30 Kelvin. For perspective, the coldest naturally occurring temperature on the surface of any planet in our solar system is roughly 33 Kelvin on the surface of Triton, one of Neptune's moons. The environment where 3IATLAS formed was colder than that, colder than our solar system's outer edges, colder than conditions we can point to anywhere in our planetary neighborhood. It formed in a place that does not have an analog in our cosmic backyard. The interstellar comet formed in a system far colder than our own solar system's history, and under very specific radiation conditions, before it was ejected into interstellar space. And that ejection, the moment when whatever gravitational interaction or stellar event flung this object out of its home system and sent it drifting across the galaxy, happened so long ago that the comet has been traveling ever since, in the void between stars, accumulating the cosmic radiation signature that Webb had to burn through to reach its interior. Now let's talk about the deepest finding, the one published in Nature on June 22, 2026, that pushed the implications of all this data to their most profound conclusion. Webb captured detailed data, including chemical ratios of carbon and deuterium, also known as heavy hydrogen, that are not found in solar system comets. The results surprised researchers. Working backward, astronomers used the components that make up 3IATLAS to understand the environment in which it formed. Deuterium is a form of hydrogen containing an extra neutron. The ratio of deuterium to ordinary hydrogen in a comet's water, what scientists call the DH ratio, is one of the most powerful tools in astrophysics for tracing where and when an object formed. In our solar system's comets, the DH ratio falls within a recognizable range, reflecting the temperature and chemistry of the solar nebula from which they were born. In 3I-ATLAS, that ratio was shattered. 3I-ATLAS contains more than 30 times the deuterated water seen in solar system comets, preserving evidence of radically different conditions in its birthplace billions of years ago. 30 times, not 30% more, 30 times more. The water inside this comet is so heavily enriched in deuterium that the formation environment that produced it bears essentially no resemblance to the conditions that gave birth to our own solar system. And because the DH ratio in cometary water forms when water ice condenses in cold molecular clouds during the formation of a planetary system, and does not change significantly during the comet's subsequent journey through space, this ratio is, in effect, a birth certificate. It tells you what the nursery looked like billions of years ago. The severely elevated DH ratio and the dearth of carbon-13 found in 3I-ATLAS not only confirms its interstellar nature, but suggests a history where it formed long ago in a less enriched, cold, heavily shielded initial environment. Less enriched. That word carries enormous weight in astrophysics. The chemical enrichment of a star system, the abundance of elements heavier than hydrogen and helium, is a function of cosmic age and stellar history. The universe began with almost exclusively hydrogen and helium. Every heavier element, carbon, oxygen, nitrogen, iron, the building blocks of planets and of life, was forged inside stars and scattered across the galaxy by stellar deaths over billions of years. The older a star system is, the fewer of those heavy elements it contains, because the galaxy had not yet gone through enough stellar generations to produce them in abundance. A system low in chemical enrichment is an old system, a very old system. By measuring specific chemical fingerprints, the first observations of this kind for a comet that formed outside the solar system, researchers found that 3I-ATLAS likely originated in the outskirts of an old star system, an old star in the outskirts of its host system. A low metallicity star is one with few elements heavier than helium in its composition, thought to have formed when the universe was much younger and less chemically rich than it is now. The team suspects that 3I-ATLAS therefore originated around a star much older than the Sun, and then the numbers arrived. 3I-ATLAS appears to have been born in a cold environment, possibly around 12 billion years ago. Our solar system is 4.5 billion years old. The universe itself is approximately 13.8 billion years old. If 3I-ATLAS formed 12 billion years ago, then it was born when the universe was less than 2 billion years old, in what astronomers call the era of cosmic noon, the period of intense star formation in the early galaxy, when stars were being born at a rate far exceeding anything happening today. Kinematic analysis shows that 3I-ATLAS is likely an object from the galactic thick disk, a remnant of the galaxy's cosmic noon period of intense star formation occurring approximately 9 to 13 billion years ago. This object is not just from another star system, it is from another era of the galaxy's history. It formed in the early universe, before our sun existed, before our solar system existed, before Earth existed, and it has been drifting through the galaxy ever since, crossing the void, waiting without waiting, until the mathematics of orbital dynamics brought it, briefly, through our cosmic neighborhood. When 3I-ATLAS plunged through our solar system in 2025 and departed in 2026, it wasn't just the third interstellar object ever discovered. It was the fastest, most inclined, and also the most ancient object ever directly observed to enter our vicinity. The fastest, the most inclined, the most ancient, three superlatives that together describe something that should fundamentally change how humanity thinks about its place in cosmic time and cosmic space. The orbit of 3I-ATLAS is the most dynamically extreme of any object yet recorded in the solar system, with a velocity at infinity of approximately 60 kilometers per second. 60 kilometers per second. That is 134,000 miles per hour. It is moving so fast that the sun's gravity barely deflected its path. It did not stop here. It did not slow down. It curved slightly, swung around our star, and continued outward. A hyperbolic flyby in which our entire solar system was a minor parenthesis in a journey that began before the sun was born and will continue until this piece of ancient ice finds some other gravitational encounter somewhere else in the galaxy, billions of years from now. And here is what that means for the question that never goes away, the question that sits underneath every discovery of this kind, that scientists are always careful not to answer too quickly and journalists always rush to raise too loudly, the question of life. Analysis of these interstellar objects is a major step toward learning how common, or uncommon, the conditions for the evolution of life are in the universe. That is a direct quote from the scientific analysis of these findings, not from speculation, not from science fiction, from the peer-reviewed research. Because the chemical composition of a comet tells you something fundamental about the planetary system it formed in, and the planetary system tells you something about the conditions that might have existed for planet formation, for water delivery, for the emergence of the chemical complexity that, as far as we know, is the prerequisite for biology. Research shows that the conditions that led to the formation of our solar system are much different from how planetary systems evolved in different parts of our galaxy. We have always assumed, at some level, that our solar system is reasonably typical, not perfectly average. We know there's diversity among planetary systems, but broadly representative of how planetary formation works across the galaxy. 3IATLAS says otherwise. It comes from a system so cold, so old, so chemically different from ours that the conditions that produced it cannot be directly compared to anything in our solar neighborhood. If planets formed in that system, and they likely did, because the ejection of cometary material through gravitational interactions with planets is the standard model for how objects like 3IATLAS end up crossing interstellar space. Those planets formed under conditions radically different from the conditions that produced Earth. Scientists say what Webb found proves that Comet 3IATLAS formed in a distant corner of the galaxy that is markedly different from the conditions found within our own solar system. A different corner, a different era, a different chemistry. And the implication that follows from that, the implication that every astrobiologist in the world is currently sitting with, is this. If planetary systems in different parts of the galaxy, formed at different times, under radically different chemical and thermal conditions, can still produce cometary objects rich in the volatile molecules, water, carbon dioxide, methane, that are associated with prebiotic chemistry, then the galaxy may be far more generously seeded with the raw materials for life than our solar system-centric models have ever assumed. The December MIRI volatile data from Webb now form the most chemically detailed record of material from another stellar system ever assembled, obtained not by sending a spacecraft across light years, but by pointing an existing telescope at a visitor that came to us. That sentence contains one of the most profound reframes in the history of space. Exploration. We did not go there. We could not go there. The nearest star is 4 light years away. Any mission to reach another stellar system with current technology would take tens of thousands of years. We have no way of directly sampling the material of another planetary system, except this. Except when another planetary system sends its material to us. When an object formed around another star, billions of years ago, travels across the galaxy on the same trajectory as chance and gravity allow, and happens to pass close enough to our sun for our telescopes to read its chemistry. This is the gift that 3IATLAS delivered, not intentionally, not because anything planned it or guided it, but because the universe is large enough and old enough that these encounters happen. Rarely, but they happen. And we were, for the first time in our scientific history, ready to receive what it was offering. Each interstellar comet brings a little bit of its history, its fossils, from elsewhere. We don't know exactly where. But with instruments like ALMA and Webb, we can begin to understand the conditions of that place and compare them to our own. Fossils from elsewhere. That is exactly what 3IATLAS is, a fossil. A frozen record of conditions that existed 12 billion years ago in a part of the galaxy that our telescopes cannot directly probe, a place older than our sun, colder than our formation environment, chemically distinct from anything we have directly measured before. And that fossil arrived in our neighborhood, briefly, and Webb read it. Distant origins make interstellar objects incredibly interesting to astronomers because they are physical pieces of other planetary systems, delivered to us on galactic tides so that they can be studied from the comfort of our own solar system. The galactic tide. That phrase deserves a moment of reflection. Our galaxy is not a static structure. It rotates. It ripples. Stars and star systems move through it on complex trajectories, pulled and nudged by the collective gravity of hundreds of billions of stellar masses. And sometimes, over timescales of billions of years, those movements deliver material from one part of the galaxy to another. Not intentionally, not precisely, but statistically. The galaxy shuffles its cards, and occasionally one lands in our solar system. 3IATLAS is one of those cards. The comet was first detected on July 1st, 2025, and spent the latter half of 2025 passing through the solar system and making its close approach to the sun. Observations have since revealed a composition unlike anything seen in our own solar system. And now, having completed its brief transit through our vicinity, it is gone. It rounded the sun in October 2025. It retreated outward through the months that followed. As of April 2026, 3IATLAS is past the orbit of Jupiter on its way out of the solar system. It will cross Saturn's orbit. It will pass the outer planets. It will reach the heliopause. That boundary that Voyager taught us is stranger than we thought. And it will cross into interstellar space again, carrying whatever secrets it still holds, receding into the dark at speeds no human spacecraft has ever reached. We will not see it again, not in any human lifetime, not in any span of time that our civilization, in its current form, can meaningfully contemplate. But it has already told us more about the universe than any previous interstellar visitor. It has told us that other planetary systems form under radically different conditions. It has told us that the galaxy's chemical history is written into the ice of ancient wandering comets. It has told us that the molecules associated with habitability, water, carbon dioxide, methane, can survive in interstellar space across timescales that dwarf the age of our solar system. And it has told us, perhaps most importantly, that our conception of what is normal in the universe was shaped by a sample size of one, our own solar system, and that the universe, as usual, is under no obligation to be normal by our definitions. Although 3IATLAS is only the third interstellar object discovered to date, that count is likely to increase as new observatories join the search. The Vera Rubin Observatory, currently coming online in Chile, will survey the sky with unprecedented depth and frequency. Astronomers estimate it could detect interstellar objects at a rate of one per year or more. If that projection holds, the era of studying one-of-a-kind interstellar visitors is ending, and the era of building a comparative science of interstellar objects, a library of alien chemistry, alien formation, alien planetary systems, is beginning. Every one of those future visitors will be another message from another part of the galaxy, another fossil from another era, another chemical fingerprint of conditions we cannot directly observe, delivered to our doorstep by the slow gravitational machinery of a galaxy that has been running for nearly 14 billion years. And the question that none of the papers quite answers, the question that sits at the edge of everything 3IATLAS revealed, is the one that has no current scientific resolution. If a 12-billion-year-old object from a cold, ancient, chemically primitive planetary system can carry water, carbon dioxide, and methane across the galaxy and deliver them intact to our solar neighborhood, what else has been traveling between the stars? How many such objects are moving through the galaxy right now, carrying the chemical legacy of planetary systems we have never seen, some of them possibly carrying something more complex than ice and gas, something that does not yet have a name in our scientific vocabulary because we have not been ready to consider it? 3IATLAS came from somewhere ancient and cold and radically unlike home. Webb looked at it, and for the first time in human history, we read the chemistry of another star system directly. Not from spectra of a distant sun, not from the reflected light of an exoplanet atmosphere, but from physical material that formed there, traveled here, and held its secrets long enough for us to ask the right questions. It is now gone. The signal is fading, the window is closed, and the galaxy continues to shuffle its deck. Somewhere out there, moving toward us, at speeds we cannot follow and on trajectories we have not yet calculated, another interstellar object is already in transit. Another fossil, another message, another piece of the universe's history arriving uninvited and unrepeatable in our tiny corner of space. The question is not whether we are alone in the universe. The question is whether we will be ready the next time the universe knocks to actually open the door.